So we're going to talk really quickly here about just a neat property that even and odd functions have in terms of integrals. So our rule for even and odd functions is that if we have an even function and we're looking at the integral from negative a to a, so it is important that we have those sort of opposite endpoints, negative 2 to 2, negative 5 to 5, for this property to work, that actually instead of finding the integral over the whole interval, we just need to find it over the interval from 0 to a, and we can double that. So the reason is that even functions, we'll write up here that we're looking at an even function, is symmetric about the y-axis. So we'll draw a quick picture of one. Say this is x squared plus 4. And even about or symmetric about the y-axis means that if we fold this on the y-axis, both sides of the graph will lie on top of each other. And if we were looking at taking the integral from here to say negative a to a, oops, didn't draw that very symmetrically, but you get the idea, that the area under this negative sort of x value portion of the graph is going to be exactly the same as the area underneath the positive x portion of the graph. So we just need to find it from 0 to a and double that area, and we'll get our total area. So to check if something is an even function, it says right here that we need negative f of x to be equal to f of x. So like, for example, with this function here, with a point, what that means is if we plug in negative 2 in for x, so we get 4 plus 4, which is 8, this is exactly what we should get if we plug in positive 2. And it is exactly what we get. We get 8 again. So no matter if we plug in a positive value or an x value, the output's going to be the same for those, pairs of positive and negative outputs. So the other part of this talks about odd functions, which says that if you plug in negative x, you get the opposite of what you get when you plug in f of x. And if you are looking at the integral over that same type of interval, so negative a to a, the integral is 0. So let's draw a little picture of an odd function. Sorry, I keep changing my pen color a million times on this one. An odd function would look something like this. Something that's true about all odd functions is that they're symmetric about the origin, which means that they all have to go through the origin. So if the y-intercept is not at the origin, it can't be odd. That's kind of the first rule about odd functions. But symmetric about the origin means that if we fold this graph on the x-axis and on the y-axis, then the graph lies on top of itself. This, for example, could be the function x cubed minus 9x. That would be an odd function. And if we want to kind of do the same thing we did over there to verify this relationship between those positive and negative x values, if we look at plugging in negative 2, we get negative 2 to the third power minus 9 times negative 2. So negative 8 plus 18. So we get positive 10. This should be the exact opposite of what we get when we plug in positive 2. And let's see what happens. We get positive 8 minus 18, so we get negative 10. So that is exactly what happens. We got the opposite output. And again, what's happening here is it's looking at, say, our area right here above the curve versus this area here that's below those curves. Those two areas would be exactly the same because it's symmetric. These x values, those x-intercepts, are at the same place but opposite signs, and so that positive area and that negative area is going to cancel each other out. So let's take a quick look at a couple examples here. So we've got the integral from negative 2 to 2 of x to the fourth minus 3x squared plus 3. So, the thing about this is that if you notice that it's even or odd, the function that you have, that's great because it makes your life easier. So this one's even. So we can, instead of finding the integral from negative 2 to 2, find the integral from 0 to 2, multiply that by 2, and we'll see here in just a second why this is advantageous. Because, in terms of finding the integral, finding our antiderivative, that part doesn't change. this is exactly what we would do if we were looking at this over the whole interval. Where this simplifies is this part right here when we go to do our f of b minus f of a, because we have a polynomial here. We're going to plug in 2 to the third plus 3 squared. And then when we plug in 0, we get 0. There, we don't have any work to do there because we know when we plug in 0, we're going to get 0 for all the terms. So basically, we kind of cut our work in half. We just have to go and grab our calculator and plug 2 in, and we get 2 times, looking at my notes here, 22 fifths is what we get from that. So multiplying that by 2 is we get 44 fifths. So again, what we found, and this is a picture of this graph over this interval, that 22 fifths was this portion of the graph. That's the area of that. And because, again, these are symmetric, when we multiply it by 2, that gives us also this portion of our graph. So let's take a look at an odd function. So we've got x plus the sine of x. So again, this is a great thing if you notice it. If you don't and you go ahead and do the integral as normal, you're going to get the same result. You're going to get, back up here, you would get 44 fifths. Here you get the same result that we'll get, which if we go back and look at our rule up here, that if we notice that we've got an odd function and we're looking from -2 to 2 or -a to a, whatever it is that we're looking at, the integral is 0. The two pieces cancel out. So really the thing that we need to verify is that we actually have an odd function. So what we need to look at is what happens when we plug in -x. Well, we get -x. Sine of -x is the same as the opposite of sine of x. That's something that's true about the sine function. And so the opposite of f of x is actually 1 times, or -1 times this function. So we get -x minus sine of x. So there it is. It actually is an odd function. And we can write on there that it's odd and that this integral is 0. So if you wanted to go ahead and find the antiderivative, plug in 2 and -2, you would get that the area under the curve here, or net area, is 0.